How you going? Chris Gargoyle here. We put years and years into redesigning, experimenting, testing torque converters to optimise performance. We're getting there. We've had at least 10 years into it. Like most inventors, we would like to claim what we do. Would like to benefit from what we do, but at the same time, through watching a lot of other people's work and stuff around the world, when things aren't disclosed and people die, all that research gets lost. So I think it's very important to, in a humanitarian sense, to disclose what we do as deep as possible, so as to help others and so things can't be lost. You have to be really dedicated. Right, so we'll have a look at an impeller here. Okay, this is a Borg Warner style impeller. The design's been around since the 50s. We've made quite a few adjustments. As you can see, this area here, I've tweaked it out. This is an area that hasn't been, I've never seen any other torque converter utilising this before. It's very much using implosion as the centrifugal force throws the fluid out. The centrifugal is mainly on the outside, the implosion's coming over the inside, where it's going to return back into the turbine again. That drag over there applies a turning force. I can't do it because I've got one hand on the camera, but if I was to put a finger on this side and a finger on the other side and just drag it, it wants to turn it. So there's a constant turning force off of this fluted edge. It just sets up a forwards bias. The other one, see if we can see it down in here. You can just see on that one there, there's a little bit of blackness on that edge of the blade. We've got a tool that we stick down in here to retweak the blades into shape, and when doing that, it actually sets up a tiny little forward step in the blade. And what actually happens is that the force running down the blade, it's like the fluid's going downhill. There's a very slight forwards bias inside here that in itself, just the fluid running through it applies a forwards force. Very good when it's all straight up like that. Very quick response on the accelerator, instant power, instant kickdown. The problem is that it lacks a little bit of drive. Drive is propulsive force forwards. So to give a bit of that, we've got some forwards blades in here. We've done this thing first on the flat and then tweaked it forward as well. And interesting enough, when the forwards bias hits this forwards taper, it really seems like to drag it. It just drags it around. So that's turning the engine, applying more force back to the engine. Now, what I've done this time around, because as I said, we've been doing it for a long time, we've done many, and we're trying to keep even the Schauberger and Nature's numbers as well, the 1.6. This one has 31 blades, so I've divided 31 by 1.6, equals about 9 point something, but the 31 being non-divisible, I've gone for 9 forwards tweaks, which gives me 8 passageways that are all going forwards, so that will give it drive onto the turbine. I'll show you here. This is the turbine and stator configuration we're going to try. I'll just give you a quick run through the stator as well. This is a new design that I haven't tried yet. Generally this in here is pretty much stock, and there is a compression there from the fluid coming off the turbine. There's a slight compression in here. It's like 1.75 flows of here have to jam through each one of these, so there's a compression. I have noticed, partly through fluke with the stator that I made, something happened and it made it go absolutely extremely well. But what I think happens is I've opened this one up, so we've got two big flows. There's 12 small flows and 2 big flows. Now generally when the fluid's ejecting off of the stator here on initial start off, it's applying a backwards force onto the stator. There's a Sprague mechanism in here, which is a one-way mechanism, so it can't go backwards, but it can go forwards. But from here, where you've got the big flow, it's just leaning on it and turning it forwards. Now doing that, the thrusts from here are being driven forwards as well, which is applying a bigger driving force back onto the engine again. And by having these two large flows, which set up like a perfect double helix, you could say, apply a good balanced force back onto the impeller. Now the turbine here, when the blades intersect this in a straight up and down motion, the fluid tucks and turns. When it's in a forwards motion, it just wants to grab it and rip it and drive it. So to have a bit of forwards is beneficial. I've also modified this edge, this implosion edge there as well, where it normally gets nothing, because it's normally just flat like on this side here, which does nothing. On this side here we've got the fluid exiting, just coming this way, wants to make it go forwards, and the fluid dipping down in wants it to go forwards. So we're picking up drive off of there. I've also got in here, it's going to be very difficult to see this one, just to tell you what I've done. Down in here I've put a tool down in here which was knocked in, and so rather than this blade just going down straight, it's now got a lump on this side, and it's like a surfer on a wave. The fluid rushing through it helps to propel the turbine even more. The other aspect of this turbine, which is what we found, is that we've modified this edge and rolled it over. It's a very low angle, but it picks up the fluid coming through here, picks up on the edge, and it's like riding that edge, and it applies a massive extra kilowatt horsepower effect to the reaction. And there's another effect that takes place initially when you're first starting and the turbine's stationary and you plant your foot. The thrust will squirt out of there at a low angle, intersecting this at a low angle. But once it comes up to speed, the angle off of here causes the fluid to vortex and rotate, backflow and rush up the blade. So it becomes centrifugal vortex motion off of the blade, which then is going to feed straight back in through the stator with multiple vortexes, applying a highly dense charge to return to the engine again, which is then going to be compressed back in through the impeller and back out onto the turbine. So we're trying to maximise every single little bit of the way, and it makes considerable performance gains. Yep, it's the future of things, especially for automatic cars or fluid drive systems. I imagine that this fluted ring here can be applied to other machines, fluid machines, in other ways, just to maximise forwards rotation from the flow itself. Yeah, so it's interesting. Well, it's interesting to me anyway. You know, I enjoy doing it. I'm into art and stuff. I love me metalwork, so we do it because we're getting good effects. You know, if you're getting good effects, you keep going and you keep doing it. Just over here we've got a late model one. This is an earlier 4-speed BTR. This one over here is out of a 6-speed ZF. One of them anyway. There's many different configurations, but this one's out of a Ford FG. As you can see in here, the stator is less blades, big open flow coming through, but at a high angle, so it's high stall. That stator there will stall it to about 3000 RPM, whereas this one is the standard one, which is only about 2200. Opening it up should reduce it a little bit more, but I don't mind because it increases the power at a lower rev, which is better than revving the thing out to 3000, depending on the application obviously. But yeah, there's a late model turbine that we've done. Fluted wave, wave down inside, you can just sort of see it in there. Okay, this is one configuration. There's many to try, and many we have tried. As far as turbines go, we've compressed it by half, compressed it by a third. Each one gives a different effect. Funnily enough, this one has 28. This one has 28 blades on it. 28 divided by 1.6 works nearly to the third. Yeah, it's a high-speed runner, that's for sure. Yeah, I'll leave it there for now. Hope you enjoyed it. If you want to give me some work, I'll do it up for you. Do yours. Because I like doing it. Okay, cheers guys.